Okay, so on this question, what they're giving us is 4 graphs, as you can see on that graph there. 2 of them are power graphs, what we call exponential graphs, and 2 of them are log graphs. So both of these two, right here, oops, both of these two are what we call exponential or power. Exponents, right? Exponents are powers. Power graphs, exponential or power graphs. These guys down here, here, I'll check my color here to be clear. These guys down here are log graphs. So you should know right away that the ones that explode, remember exponential graphs explode upwards, those are power graphs, exponential graphs. The ones that go really low are log graphs. Now, why? Because remember what we've been learning in this section all the way through? Logs are the opposites of powers, aren't they? They're the inverse functions, like we studied inverse functions back in section 5.1. That's why we started with inverse functions, because we knew we were going to get to logs and exponentials, which are the prime example of inverse functions. So logs are exactly the opposite of exponentials, of power functions. So whatever a power function does, the log will do exactly the opposite. All right, so with that in mind, that'll guide us through this problem. So these are power functions, exponential functions. They're blowing up, right? And these are logs. They're staying low. Okay, so then how do you know which one's which one? Well, something else you need to know. Notice this right here. This is right here, e to the x. Let's look at the two. Let's look first off at the 2 functions that are the power functions. I'm going to leave the logs for a minute. We'll get to the logs next. Let's first start with the 2 power functions. So these are the 2 functions that have x up in the power zone, right? Called exponentials. X is an exponent on these 2. These are going to be these 2 for sure, right? These 2 are going to be these 2 power functions, exponential functions. We just got to figure out which one's which one. And the other 2, the logs, are going to be these other ones down here. Okay, well, how do you know which is which one? Well, the bigger, so for exponential, let me write the rule for exponential. Exponential power graphs. Here's the rule. Higher base goes up faster. Bigger base, obviously bigger base. It just sounds more catchy. Bigger base goes up faster. Smaller base goes up slower. I mean, it's pretty simple. Well, how do you know which one's bigger? Well, we have e to the x and we have 10 to the x. Now, you probably aren't totally familiar with that e. You know, what is that e? It's e. Well, e is a special number, just like pi. You guys know pi is 3.14, blah, 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 blah. It's a special number that we use in geometry. It's the ratio of a, well, anyway, it's the ratio of the circumference of a circle to the diameter. Anyway, e is a special number as well used in calculus. What is it? It's 2.71, blah, 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 blah. So all you need to know is e is a special 2-something number, like pi is a special 3-something number. If you just know that much, you'll be good to go. Just remember, e is a special number. It's 1 lower than pi. It's 2-something. And pi is 3-something, right? Both special numbers that we use in higher math and science. So what? Okay. Well, that means this e to the x is basically 2.71 to the x. How does that compare with 10 to the x? Which one's bigger? Well, clearly 10 to the x is bigger. 10 is bigger than 2, right? So 10 to the x is the bigger one. So therefore, this one over here must be the 10 to the x, and the other one must be the e to the x. Because the 10 to the x is going up faster, isn't it? Because it's the bigger base. That's the one going up faster. And notice how it's coincidentally the exact right color. The black one is the black graph, and the green is the green. So whatever pen color you use, that's the end. I'm just joking around. I already knew what it was going to be, so I used the right pink color. Sorry, just joking around. A little math joke there. There's not a lot of funny math jokes. I got to do what I can, you know. All right. So so next, let's do the two logarithm graphs. So the other two are logs. How do we know which one is which one? Well, let's remember that here. Let me write down here. Log graphs. What are logs? The inverse of exponentials. They're exactly the opposite of exponentials. They do the opposite. Okay, well, what does that mean? Do the opposite. Well, look what exponentials do. Bigger base goes up faster. Oh, wait, let me first show you. I haven't shown you anything. So we have log of x, and we have ln of x, don't we? So what does that mean? Notice, and you might not be totally familiar with ln. We've had it before. This stands for natural log. It's like, it's logarithmic natural. It says it backwards, basically natural log. Anyway, so what? Well, remember, every logarithm is supposed to have a base, isn't it? Notice those two logs, and ln is a log. It's just a special log, the natural log. They don't have a base. What's up with that? Well, there's two understood bases, kind of like, you know, like if I write x and I don't put a power, it means one power. That's the kind of thing we're talking about. So basically, when you write the word log and you don't show the base, it means 10. So you just have to know that. It's called the common log. Basically, in the world of science, when they do stuff with logarithms, they use base 10 so often that after a while they said, look, if I don't write anything, you know I mean the base is 10. It's, you know, just shortcut over time, like any field naturally does over time. So just they use base 10 so often that after a while they said, look, that's the common one. If I don't write the base, just assume it's 10. It just kind of caught on. And so if you write the word log and you don't show the base, everybody knows it's a 10. Okay, well, what about the other one? The other one's not showing space too. Yeah, well, this one is a natural log, as I said. It's different. It's not the common log, right? It's ln, not log, right? Okay, so what? Well, that means it is base E. That's that special number, that 2.71, blah, 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 blah number. It's actually very special. We do stuff with it in calculus, and finance uses it for compound interest. Anyway, higher math and science use it a lot. It occurred in nature. That's what we call it, the natural log. It's part of how things work in the created order. So anyway, E, it's basically, so you need to know, if they ever write the plain word log, and don't show the base, it's 10, called the common log. And if they write ln, which stands for natural log, kind of backwards, logarithmic natural, the base is E. So every log has a base, really. There's no such thing as a log without a base. It's just these two don't show their base naturally. You have to fill them in. Okay, great. That's a long story to say this is base 10 and this is base E. So what? Well, remember what exponentials do now. The bigger the base, it goes up faster. So how's that going to work for logs? Well, they're the reverse. Remember, they're the inverse functions of exponentials, the opposite. So what does that mean then? Instead of bigger base going up faster, it's going to be the reverse of that, isn't it? It's going to be bigger base goes up slower. Bigger base goes up slower. It's the reverse. They're the reverse. So what are the bases we're talking about? Right here, the base of 10 and the base of E. And you know E is 2.71, blah, blah, blah. So which one has a bigger base? The log base 10. This one is bigger. Oops. Bigger base. This one over here is a smaller base. So the bigger base goes up slower. So that means the regular log x is going to go up slower than the natural log. So which one's going up slower? The blue one is going up slower, isn't it? So that one is got to be the regular log. And the red one has got to be the ln because it's got the smaller base, so it'll go up faster. It's the reverse. And so there we go. Does that make sense? So it's all about exponential and log. Exponential functions are those with powers, and they blow up. The bigger the base, the faster it goes. You know, E is 2.7, and that's smaller than 10. So the 10 is the bigger, it goes up faster. And then when it comes to logs, it's exactly the opposite because they're the reverse of exponentials. And so you need to know that ln has a base of E, natural, the E, 2.7. And regular log, if it doesn't show its base is 10, every log really has a base. And so the 10 is the bigger, which means that one goes up slower because logs are the reverse. Bigger base goes up slower for logs. And so there we go.